Is the mic on? Yeah, okay. Okay, shall we get underway? So, there was a question when I went through the solution of question of day 12 last Friday, where somebody said, but that's not what you wrote in the spec. Do you remember this? It was about the direction of the sign. And the spec is actually correct. The difference is the spec used one of these formulations, and I used the other formulation in the slide. So the point of the question 12 is that the order of the values is not consistent with the order of the indices. And you can say that this way, or you can say it this way. So when you got your question of the day feedback, do you guys read the autograder feedback? Do you look at that? Yeah? Okay, so there's usually a pretty extensive, or often an extensive discussion of what's going on. I put that in for the question of the day feedback, so if you're still confused, go back and look at you should have received the PDF. You're still getting these PDFs, right? So you should look at the PDF and see what the autograder says. All right, question day 13 was due today. We're going to look at it in a second. Question day 14 is released at 11 o'clock as usual. It will be due on Wednesday before class. Lab 7 is going to be tomorrow, and you should expect homework 2 by Friday. We're behind with homework 1. It's turned out to be quite tedious. I don't actually grade homeworks. I write the autograder for the homeworks, and I run them through. And then I let the TA scan all the homeworks and grade individual functions. It's quite tedious. And it's even more tedious when people's code is very different. And there's apparently quite the grab bag in some of the functions. So it's taking them a little bit longer, but we hope we get it done today or tomorrow at the latest. Okay. Where were we? Question day 13. So in question day 13, I asked you to write a function called randinsert, which essentially takes a list of elements and randomly removes an element from the list and reinserts it elsewhere. Now the whole point behind randinsert is we looked at the Fisher-Yates algorithm for shuffling. That was our function scramble from the first homework was a shuffling function that is essentially identical to random.shuffle, except that we wrote this one. It's called the Fisher-Yates algorithm for shuffling fairly. It has a couple of properties. I think we discussed this in class, that every permutation can be derived by this shuffle, and that every permutation has equal probability to be the outcome for that shuffle. Now we're going to create a new algorithm, a new function that does the same thing but doesn't have those same kinds of guarantees. And I thought it would be fun because we have this inversion index we can use to compare the performance in terms of how thoroughly it shuffles compared to, say, scramble and so on. And the idea here was that you're going to take a card, you're going to remove it, and then you're going to put it in. So it's like pick a card, any card, and then reinsert it in the hand somewhere. And the key part of the spec was that you're going to modify the input list L. You're going to modify the input list L to create the permutation. So this was kind of a tricky question because list comprehensions, which build new structure, and concatenation, which also builds new structure, you can't use those, right? So the assignment itself was by saying you were supposed to modify L should have made you aware that be careful that the things we often use for lists will probably steer you wrong. So we know we can modify list structure using assignment to slices, like we did even in the scramble function. We didn't use assignment to slices, but we used contemporaneous assignment to exchange elements in the list, and that's destructive. So we could approach this using list structure. Here we want to remove and insert, and we can use modifications with slices, but some of the index calculation is tricky. So let's take a look at how we might approach this. So when I'm coding a function like this, I might sit down to the Python REPL and just try a few things. So what I might do is I might create a list like this one, and then I might say, well, let's see what happens when I assign the empty list between elements 3 and 4, so 0, 1, 2, 3, and 4. And what happens when I insert 100 between elements 3 and 4? And what happens is what you expect. The first one blows away the 50, and the second one replaces that with 100. And this, by typing L here, I can see I've modified the list because now the list has changed. So yes, I can use slices here and assignment to slices. I can even assign a new element before the first element, and I can even assign a new element after the last element, which is between length of L and length of L plus 1. And that gives me kind of what you expect, right? This adding stuff to the end with assignment is always a little tricky. Be careful with -1s. It doesn't always behave the way you want it to. So I could probably write a code. I need to be careful with indexing, and the corner cases can be a little tricky, so I need to test thoroughly. But there's another, and I have to be careful with randint, because remember when we introduced randint, I told you this is one of the few Python functions that uses inclusive indexing. So when you say randint ij, you're asking for a random integer between I up to and including j. Unlike with range and all the other indexing schemes, randint uses inclusive indexing. So it's a number between I and j inclusive. So all of this is surmountable, right? You could sit down and write this function, but there was a big hint. And the hint was, consider looking at your list methods again. So I assigned the list methods chapter months ago, but this is an example where it's useful to go back and see, look at your cheat sheet or go back and see the assigned chapters, reread them because you'll see stuff you didn't see the first time. There are list methods that are exactly configured for this. So using randint to generate a random index, I can use the pop method to remove the kth element destructively, modifying L, remove the kth element, and return whatever the value of that element is. So this pop method returns a value, which is the element that I've just removed. So this is exactly akin to picking a card from a hand and removing it and having a pointer to the card itself. The insert method takes a position k and an element to insert. So I can combine these two with the appropriate calls to randint to remove a random element and reinsert it in a random place. So there's the function. I import randint from random. I'm going to do a certain number of repetitions, default 1. And what I'm going to do here is the first, remember I have to evaluate these two arguments to insert. So I come up with a random number and a random number here. The first one here, randint 0 length L minus 1, this gives me a number between 0 and length of L minus 1, inclusive. A random number, that's the element I pop. Okay? And that element that gets popped is the value that I'm inserting into the list. This other element here, random integer from 0 to length of L minus 2, this is interesting here. We're going to talk about this in a second. This is where that element I pop gets placed. Now the only funky thing going on here is what exactly is the length of L? Because the length of L at the beginning of, before we start, is whatever the length of L is when I pass it in. Here, I'm assuming that the length of L has not changed. But here, I'm reducing the length of L by 1. And it has to do with how the arguments are evaluated. So, let's see. I have a method, insert. It has two arguments, argument 1, argument 2. These arguments are evaluated left to right. So the first argument that I actually evaluate is this randint. And I have to be careful that I subtract 2 from the length of L, the original length of L, because otherwise I may end up, by chance, trying to insert this removed element in a location that no longer exists in the list, one beyond the end of the list. So this length of L minus 2 here is evaluated before the length of the list is changed by the pop. You understand? So it's because I'm evaluating these left to right that I have to subtract 2 from this length of L. If I had done this, as some of you did, where you say x equals this, the value here, and then inserting it, I would have been able to do length of L minus 1 because L would have changed and the length of L would have been evaluated after that change. As it stands, length of L here is evaluated prior to the pop, and I have to account for that. So they can be tricky here as well. But this function satisfies all the criteria. It's fast, it's clean, it's short. Basically says, do this R times, just pop an element and reinsert it. Just keep doing that. And at the end of the day, return L, which has been modified. And we could examine, actually it would be kind of fun to take that inversion index function that we did in a prior question of the day and test the inversion index on an ordered list after 1 reversal, after 2 reversals, after 3. You would see the inversion index go rapidly from a 1, which means that the list is completely, what is a completely ordered list, right? Yes, I think. I don't remember what the directionality was. But going from whatever, either 0 or 1 for a completely ordered list, and gradually changing as you do more replicates of this random removal insertion. Okay, any questions? Okay. So when last we met, we talked about selection sort. We sort of understood. We did an algorithmic analysis that let us understand that selection sort is order n squared. This was a summary of what the order n squared was. We did some implementation and testing. The selection sort does have that runtime behavior. Remember that curve grew. It had that sort of that quadratic shape. And then the question is, were there other sorting algorithms to do better? And at the end of the day, I showed you a little excerpt from the Algorithmics website. By the way, I gave you the Facebook address. The YouTube address is actually a better address. You can get all the dances there. So anyway, so it's kind of fun to watch, and it's a little mesmerizing. Okay, so this is where we were. Today we're going to try something else. We're going to look at a new algorithm called quicksort. Now, quicksort, like selection sort, like insertion sort, like bubble sort, is what we call an in-place sorting algorithm. So an in-place sorting algorithm is an algorithm that performs on a list by modifying it. In other words, it requires exactly the memory space you need to store the original thing you're sorting. There are some other algorithms, like merge sort, which require that you have a second copy of the original list. So it doubles the storage requirements. That comparison is not particularly fair. This algorithm is a in-place sorting algorithm that has runtime that is better than selection sort on average. You remember that I talked to you last time about how it's one thing to say the algorithm is order n squared. It's another thing to say that the problem itself is order n squared. So I can say something about a particular algorithm. This algorithm requires n squared time, where n is the length of the input. But I can also, forget the algorithm, I can say something foundational about the problem. Sorting something in place requires at least order n squared amount work. And if the amount of work it requires and the amount of work done by the algorithm are the same, then you can stop looking for a better way to do this because you've got an optimal solution to that problem. This is something you're going to hear over and over again in CS2 and then in algorithms. This is the name of the game. Now, it turns out that sorting is not an order n squared problem. Selection sort and insertion sort and bubble sort are order n squared algorithms, but the sorting problem itself is actually order n log n, which is less than n squared. So what that means is selection sort is fine, but there exists a better algorithm. And the better algorithm everybody cites as the optimal algorithm is an algorithm called heap sort, which is pretty complicated, so we're not going to do it in this class. So what I'm going to show you instead is an algorithm called quicksort, which has that same kind of n log n flavor when everything goes right. And then we're going to look at quicksort, we're going to analyze it, I'll show you its n log n, but I'll also show you that when an assumption fails, quicksort becomes n squared, like selection sort. So in the worst case, quicksort is no better than selection sort, while heap sort in the worst case is better. And then finally, I'm going to introduce how we can use randomness to improve the runtime of an algorithm that will patch quicksort and make it on average an n log n algorithm. So we're going to start this little odyssey from our analysis of selection sort being n squared. We're going to look at a new algorithm called quicksort, which on average is order n log n when a certain assumption is made. And then when the assumption fails, it's also n squared. And then I'm going to show you how to use randomness to counter that assumption, the failure of that assumption, and make it n log n again. So this is the game plan. So let's do this a little bit at a time. If you get confused, stop me because it's important, and you should be able to understand this. So I want to make sure I get it across. So this quicksort algorithm is a good example of a type of algorithm that's called divide and conquer. Now we've seen a divide and conquer algorithm. Anybody have an idea what that might be? What's the algorithm we had that chopped stuff in half? Binary search. That's a great example of divide and conquer. Divide and conquer says you have a big problem, divide it into two smaller problems, and then solve the one that matters. And quicksort has a slightly different take on that, but the idea is you have a big problem, you divide it into two smaller problems, you solve those problems, and together that gives you the solution to the larger problem. It's a general algorithmic idiom. It's a way of approaching a problem. So imagine if you take a list that's not sorted, and you could magically partition that list into two lists, a top half and a bottom half, where the bottom half had all of the smaller numbers, and the top half had all of the larger numbers. So in other words, I could go from a random list like this to a random list with all the smaller numbers on the left and all the larger numbers on the right. They're still not sorted, but they are more sorted than the first list. So imagine that I could snap my fingers and take any random list and turn it into a list that had this property. Okay, that's the first step. If I could do that, then this suggests a sorting algorithm that repeats this. So neither half is sorted, but they are distinct. All of these elements are less than all of these elements. And this suggests that I could, if I could somehow sort each half, then the whole list would be sorted. Why? Because if all of these guys are less than these guys, no matter what order they're in, if they were in sorted order and these guys were in sorted order, then the whole thing would be in sorted order. Does everybody see that? Right? So if I could somehow get through this first step, I'd essentially be done, provided I could then somehow sort the two halves. Well, the answer is, so here's the thing I was just claiming. So here's the original list that's been partitioned. And then imagine that I could somehow sort this left half and sort this right half, and then I could just remove the bar and they're sorted. Okay? That's the general strategy. So how do I sort those two halves of the list? Well, this is easy. This is a recursive algorithm. So however I manage to sort the outer half, I'm going to sort the little halves. Basically, I'm going to snap my fingers and partition those sublists each into two smaller sublists of smaller numbers and larger numbers. So let's see. So here's my original list, and I managed to do that magic partition there and there. Now imagine I take this guy and I somehow magically partition it into smaller and larger numbers. And the same thing here, I magically partition this upper half into smaller and larger numbers. Now these may not be sorted within the lists, or they could be, we don't know, but they're not necessarily sorted between the lists. But I'm just basically repeating the pattern. I'm going to take every sublist, I'm going to chop it in half, smaller, larger numbers. And at the end of the day, when I get here and I cut those lists in half, I now have lists that are all of length 1. And remember, a list of length 1 is always what? Always in order. It's always sorted. No way I'm not sorting a list of length 1. One element, it's in order. So when I get to this point, by recursively chopping this in half and addressing each half a bit at a time, eventually the halves all become of size 1 so that they're individually ordered, and I can just remove those arbitrary partitions because the whole list will then also be ordered. Okay, so I wave my hands over this because the clear thing that I didn't tell you is how I got from here to here. So the transition from an unsorted list into a list that's partitioned. I told you I was going to snap my fingers. Snapping your fingers isn't a good strategy. You have to come up with an algorithm for that. That algorithm is called the partitioning algorithm, and it's in the important part of quicksort. Now, I'm going to caution you, the quicksort dance that the algorithmics people do is one of the most elegant dances. If you want to watch it, it's really interesting. However, it uses what was the original partitioning algorithm, sometimes called the pivoting algorithm, that quicksort originally had. I'm going to show you a simplified partitioning algorithm that I think is easier to understand. The downside is that what I'm going to do here will not exactly match the algorithmic stance for quicksort. So be aware that theirs looks a little different than this one. But I think this is a lot clearer to understand. So we're going to do things this way. All right, so we're going to partition that length n list into two hopefully even sublists with doing a linear amount of work. So that suggests I'm going to take my jumbled list, I'm going to scan it, and maybe do some modification. And at the end of that scan, which will take order n amount of work, I will have the list partitioned into a lower half and a higher half. That's the sort of general scheme of things. And recall from our discussion of binary search, thank you back there, whoever remembered it was divide and conquer, that you can divide something of size n in half by, divide something in size of n by 2, order log n times before you get to something of size 1. So this suggests that if I can make this partitioning step here be order n each time, order n, order n, order n, and the division happens log of n times, so log to the base 2 of 8 is in fact 3, so 1, 2, 3, then this algorithm takes 3 times order n, which is log n times order n, or n log n time. So that's where the runtime analysis takes us. I'm going to be doing logarithmically many partitionings, and each partition is going to cost me order n work, so logarithm of n times n is n log n. Right? Everybody got that, more or less? So here's my little analysis. Every time I partition this thing is order n work, and then by rule 3, this recursive sort of iteration, this recursive repeated partitioning will happen logarithmically many times, so the algorithm itself will be order n log n. So it begs the question of how do I do the partitioning in order n time? So how do I go from this unordered list to this pseudo-ordered list where I have a partitioning element that divides smaller elements from larger elements? That's the question. So we're going to see the partitioning algorithm now. So the idea is I'm going to pick a value that seems to represent a reasonable middle value. So I have this list, 100 elements. I'm going to take a pivot value, say of 50, and I'm going to scan the list, modifying the list so that elements below 50 end up on the left side and elements above the 50 appear on the right side. And that algorithm, that partitioning algorithm, is called a pivoting algorithm because I'm pivoting about that middle value. So how do I pick a pivot value? I don't know what the middle value is. Sure, I could scan the list and do some calculation to find the mean value, or actually the median value of the list, but that's going to take a lot more than order n time. So I'm at an impasse because there's no way of doing this efficiently without using up computation time that will make my calculation overall slower. So the answer is, because I have no information about what these values are, and I caution you, in my example, I'm just using the numbers 0 through 7. Sorry, I'm using the numbers, I'm missing a number in there. I'm using numbers 0 through, I don't have a 4 up there. So I'm using numbers that are all sort of unique and small, like it was a deck of cards. But this works on any list, even numbers that have no pattern, between a list of 8 elements chosen at random from 0 to 1,000,000. This works fine. So I don't know anything about the values. So when I don't have any information about what the values are, what a statistician does is they pick one at random. So that's exactly what we're going to do. We're just going to assume that the 0th element of the list is my pivot element. On average, that 0th element of the list is going to be a middle value, or close to the middle, on average. That's the way random selection works. So I'm going to choose L0, which is 5, as the pivot value. That says 0 is the pivot point, 5 is the pivot value. And now what I'm going to do here is very much like in selection sort, I'm going to iterate over the remaining elements here and compare each one of these guys to that pivot value. So the general idea is you scan the list comparing every element to the first element. And by the way, if I'm scanning the list of length n and comparing it to the first element, I'm doing order n work because it's order n comparisons, right? So keep that in mind. And I'm going to do this by keeping a separate pointer here. So here's a little picture of what my list looks like. This is going to be my pivot value. And I'm going to start with 2 pointers. So I is going to be allowed to range from 1 up to the length of L minus 1. So I will take, this is supposed to be a right arrow here. I is going to move left to right starting at position 1. We're going to scan through all of these, and each time it's going to compare to 5. It's going to compare 8 to 5, 1 to 5, 3 to 5, and so on. And this second little pointer here, M, points to the pivot value. Now, as I step through this list, I'm going to be comparing the element at that pointer, at I, with the element in the first location, the pivot value, and it's either going to be larger than or smaller than. And depending on the outcome, I'm going to do something else. And since the only thing we know how to do is to exchange elements, that's exactly what I'm going to do. So let's just walk through this. So when the value that I'm comparing, like 8 is greater than 5, I don't do anything. I just let I advance, I go on to the next element. So 8 is greater than 5, so I advance I. But when the value is less than the pivot, so 1 is less than 5, what I'm going to do is I'm going to advance M. So M, which was pointing to location 0, is now going to point to location 1, and I'm going to exchange 1 and 8. So I advance M, and I exchange 1 and 8. And now I'm ready to go on and check out value 3. So I advances. Now I'm going to compare 3 with 5. 3 is smaller than 5, so what do? Well, I advance M and swap. So M will go here, and I'm going to exchange 3 and 8, and you can see how this process works. So let's see the whole thing. So here's my beginning, starting value of my list. The pivot value is the 0th location. The middle pointer starts at 0, and I starts at 1 and ranges over the rest of the list. After the first comparison, there's no swap because 8 is larger than 5. In the second comparison, 1 is smaller than 5, so I will swap, which advances M and exchanges 1 and 8. Right? You saw that, right? So there it goes, just like that. The next step through, I advance I again, and 3 is less than 5, so I'm going to have a swap here, which will advance M and exchange 3 and 8. Next step, 6 is larger than 3, so I don't do anything. I just advance I. 2 is less than 5. I'm sorry, I should have said 6 is greater than 5. 2 is less than 5, so I advance M, I swap, advance M, and exchange 2 and 8. There it goes. Now I go on to the next step. 7 is greater than 5, so there's no swap, so I advance. And then final pass, 0 is less than 5, so I advance M to here and exchange 0 and 6. There they go. And I'm done. Now, one last step. When I'm done, wherever this M ends up, I'm going to take that value and exchange it with 5. Now, this last step acknowledges something. If M is used to sort of advance through the list anytime there's a number smaller than 5, what it means is at the position of M here, all of the elements smaller than 5 are over here. In other words, the number of elements to the left of it is exactly how many elements are less than 5. And the actual real location of where 5 should end up is where M is. So when I swap those, 0 and 5, I know that 5 is in the location where 5 should be once the list is sorted. That 5 has found its home. It's permanently there. And on the left to the left of it are all the numbers that I've advanced over because they're smaller than 5. And that means by exclusion, by what's called the pigeonhole principle, all the numbers to the right of the final location of 5 are larger than 5. All right? So you have to work this out for yourselves. Pull out a deck of cards, lay out 8 cards in random order. Use something to point for I and M, walk through it, and convince yourself that this really does work. Regardless of what that first pivot element is, you will end up with that pivot element in its final location and all the elements smaller than it to the left and all the elements larger than it to the right. Okay? Now, if you have duplicate elements, like multiple 5s in the list, you have to decide whether you're going to have numbers to the left be less than or equal to 5 or strictly less than 5, and concomitantly numbers to the right will be greater than or equal to 5, and that's fine. Just make a consistent choice. Is this sort of clear? So let's write the code. Actually, let's do this one more time. So I'm going to do this again, but this time I'm going to do it on a whole list, and we're going to do the whole recursion, I believe, and see how we end up handling everything. So here's my original list. Here's how it ends up after the first pass. The 4 will end up in its 4th location. The 1, 2, and 3 will end up to the left, 6, 7, 8, 5 to the right. Here is my function. It looks a lot like binary search. It is a recursive function, has a recursive helper function, just like binary search did. The only thing Quicksort does is it calls the helper function. And you'll notice the value of the list here, L, is available within the scope of the entire function. So when I call qsort on L, what I do is I invoke the helper function with the minimum index and 1 past the maximum index. So these are just a range of L values. And the helper function takes a low and high pointer. So low and high, just like this. And it says if low is less than high, which it will be, pick the pivot value to be whatever is at low, position low. Pick the middle value to be the same. The middle value is the M pointer. It's going to start in the same location as the pivot. And then I'm going to let I range from low plus 1 up to, but not including high. And if it's less than the pivot, I'm going to do that swap. And at the end of this loop, I'm going to exchange low and mid with mid and low. Remember that last swap to put the pivot element in its correct position. And then I'm going to recursively sort from low to mid and from mid plus 1 to high. Mid plus 1 because whatever is at mid is already known to be in its correct location. So this is my recursive sort. This is the pivot part of the algorithm, which we can see by analysis. We have I going over a range that is less than the length of L. This is going to be done order n times, and there's nothing in here that is more than order 1. So that's an order n pivot algorithm. The recursive cost brings it up to n log n, occurs when I recursively sort on the helper functions. Okay, so this is, you can study this on your own. If you like, I'll post the code. Just let me know, I can do that. Let's have a little bit of fun and see how well it works. So I'm going to do a comparison of the 2 implementations and do some empirical testing, basically. So I'm going to import the random library. I'm going to import a library called time, which I think we've seen before. It's what lets us time run times of code. And a new library called the matplotlib library, which is going to let me do some plotting. That's how I'm going to get some diagrams to see. And I'm going to import the pyplot part of the matplotlib library, and I'm just going to call that plot so that I can save some typing. So my first function is called randlist. It takes a size n, and what it returns in this very simple comprehension is a list of n random integers chosen from 1 to n. Now notice that this list has duplicates in it. It's okay. All right? We'll handle duplicates. Now, the second thing I'm going to do is implement a list called timesort, which is kind of interesting. It takes 2 arguments, and what it does is it stores the current time, then it does the sort, and then it returns the difference between the time at the end of the sort with the starting time. So basically it takes the time difference. What time is it now? Do my sort. What time is it at the end? That difference tells me how long it takes to do the sort. But what's really cool about this function, let me see what's different about this function. I might have said it right here. This sort is not really a function. It's used as a function here, but I don't know what sort actually is. And we're going to use this function where we're going to give as the argument the name of the function that we want tested, that is a sorting function. So this time function can be used with selection sort, it can be used with insertion sort, it can be used with quick sort, just by saying and passing as an argument the name of the function I want to sort with. So that's pretty cool. Let's see how that works. First thing I'm going to do is I'm going to generate test data. So I'm going to have a value D, which is a list arranged from 1,000 to 10,000 by 500. So 1,000, 1,500, 2,000, 2,500, and so on. And then S is simply going to be my random size list N. Remember my rand list, which gives me for size N, gives me a random list of that many numbers for N and D. So this will give me a list of lists, and that list of lists are all random inputs to sort. Random lists of numbers of varying sizes. I'm going to then, with two more comprehensions, I'm going to collect the results of this time sort. And remember, time sort returns elapsed time. It returns a time measurement. The first time, I'm going to use selection sort as this function. Notice that selection sort is a function definition. I'm passing it like a value. And I'm going to run selection sort on the list L for every L and S. Now, why am I wrapping this in a list? Because I don't want to destructively modify these lists here. I want a new copy of the list. So that's a copy of the list L. I do that because if I sort them in the first call, then when I try them with quicksort, it'll be really fast because they're already sorted. So this makes sure that they both compare on the same thing. So this is the list of runtimes for selection sort, list of runtimes for quicksort. And then here I've got some calls to my matplotlib library. I say plot.title is sort comparison. The X label is N, which is the size of the list. The Y label is elapsed time in seconds. Then I'm going to plot the times of selection sort and the times of quicksort against the sizes of my data. I'm going to label that selection sort and quicksort, and I'm going to plot the legend at the top. So it's going to show me the legend and then plot show, and this is what I get. So here's the legend. You can see the data sizes here and the elapsed time in seconds here with the appropriate labels and the title of the plot. Looks very nice. But what do you notice? You notice that selection sort has that very typical growth curve, but look at quicksort. Quicksort is not quadratic. Quicksort is order n log n, which is slower than n, but it's a lot faster than n squared. It's really astoundingly fast, right? I mean, here we're sorting lists of 9,500 elements in a less than what is maybe a hundredth of a second. We're way down. Whereas selection sort is up here taking way over a second. There's a 100 or 1,000 time advantage. These kinds of differences between n squared and n log n, they really matter. So if you get nothing else from this lecture aside from divide and conquer and quicksort, remember this plot. This should convince you that paying attention to algorithmic runtime has enormous payoff. It's what distinguishes a computer scientist from somebody who just writes code. You really need to pay attention to this. It's interesting too. Let's dive a little deeper. So, the cost of the pivoting part, we've already talked about. It's clearly order n. It's a scan of the list with some exchanges. The cost of quicksort does seem to be order n log n, which in fact sort of is borne out by this empirical test. But what happens to quicksort when the list is already sorted? Will it be n log n? Will it be faster or will it be slower? What do you think? So remember how quicksort works. It does the pivoting part first, and then it does the recursive formulation. The recursive part will be the same. I'm going to recursively call myself n log n times. The pivoting part will still be order n. But the recursive part, the fact that we're calling ourselves logarithmically many times, depends critically on an assumption that that pivot value is going to be roughly, on average, in the middle of the list. Remember, we made that assumption. On average, if you don't know any information, it's roughly in the middle of the list. The problem is, when the list is already sorted, will that pivot element, which is the first element of the list, will it be roughly in the middle of the list? It won't be. And when your pivot element is always the smallest element in the list, instead of getting two nicely even-sized sublists, you get a list of size 0 and a list of n-1 size. And that means that the recursive calls will occur not logarithmically many times, but will occur n-1 times. And n for pivot times n-1 recursive calls is order n squared. So quicksort is order n log n only if everything goes right. If you have a list that's sorted or almost sorted, the runtime of quicksort rapidly degrades and becomes the same as selection sort, or has the same growth rate as selection sort. So the problem here is that pivoting needs to divide the list approximately in half to get that logarithmic advantage. If we're not dividing it in half reliably, we're screwed. That's the problem. So here's a genius solution. Because sorting lists that are already sorted, or sorting lists that are mostly already sorted, is not uncommon. I can't tell you how many times I've resorted you in my class list by last name, constantly resorting. Few people add, drop, whatever, so there's some small changes on the margins. But by and large, the list has been sorted since the beginning of the class, and it only gets marginally reshuffled. So sorting a sorted list or a nearly sorted list is actually very commonplace. So we need to beat this somehow. And the answer to beating this is, let's choose, instead of the first element as a pivot, let's choose a pivot at random. If my list is sorted already, or if my list is unsorted already, by adding that extra non-determinism, that extra random choice, on average, I'll get that average middle of the element of the list behavior back. So here's my function again. This is just a helper function. It's just like the first one. No difference except this line. Basically, it says, instead of assuming the pivot is the first element, pick a random integer between low and high -1 inclusive. Careful, it's randint, inclusive. And the first thing I'm going to do is I'm going to take that random element and put it in the 0th location, exchanging it with the 0th location. This ensures that the pivot in location 0 is always a randomly selected element of the list. It's the only change to the algorithm. So what does that do? Well, here's randomized quicksort. That's what we just talked about. You can see that it's got essentially the runtime behavior of quicksort. It's a little bit slower because it has to do a little bit of extra work. It's always randomly moving stuff around. But what's important here is that the rate of growth, the shape of the curve, may be a little slower, but the shape is the same. And remember, runtime analysis is all about the shape, not about the actual values. So the shape here is that randomized quicksort does almost as well as quicksort and has the same rate of growth as n gets bigger. And it also easily beats selection sort. And this is done on randomized lists. What happens, so let me just zoom in a little bit. So now I'm going to do a more densely spaced randomized list. You see that there is a little bit of a difference, but that the shape is still the same. And by the way, if you call your attention way down here, list of size 100, quicksort actually appears to be, randomized quicksort actually appears slower than selection sort. Because we're only interested in the rate of growth, but in actual runtime, randomized quicksort is beaten by selection sort for very short sequences. Turns out that the quadratic cost of selection sort only really gets in the way as the number n gets larger, and that's the whole point of this kind of algorithmic analysis. We don't care how long it takes to solve a problem of size 10. It's going to be fast regardless of what you do. We do care when that problem is the size of million or 10 million or a billion. Then we really care. And that's where algorithmic analysis can steer you the right way. Okay, is everybody okay with that? So zoom in, we can see the behavior is still, you can see this space a little better. But what happens when I look at lists, input lists that are sorted instead of randomized lists? Well, look what happens. Here is selection sort. It's at the very beginning of that curvature up. This is randomized quicksort. It's still the same. And this is quicksort when it has its worst case behavior. Quicksort is not only quadratic like selection sort when the lists are sorted, but in actual runtime it's worse than selection sort because it's doing more work than selection sort does. It's doing extra pivoting. It's doing extra. The partitioning algorithm itself is not the easiest thing in the world to do. It's not always fast. So what's the lesson here? The lesson here is that paying attention to algorithmic runtime pays off as the size of the problems you solve gets larger. And that when things don't work out, randomization, or what we technically call non-determinism, is a valuable tool to make your code run faster, or can be a valuable tool. We saw a randomized algorithm in class earlier. In fact, we saw it on the first day of class. We talked about the matching algorithm. And you remember that I told you that when I picked a man to propose from the pool of unengaged men, I picked one at random. And I also told you that depending on which one I picked, the outcome might be different, but would still share that same, no swapping makes people happier property. So that was an example of randomness that led to different solutions and possibly different runtimes, but didn't really change the outcome of the algorithm much. This is an example of using non-determinism to avoid bad behavior when you know bad behavior can happen in the worst case. It doesn't take the bad behavior away. It's still possible that for a particular list, ordered exactly the right way, some randomized list that's ordered exactly the right way, and some exactly the same correct sequence of random pivots, I will still observe an order n squared behavior, even with randomized quicksort. But the chance of that happening is vanishingly small. All the moons and planets and stars in the universe have to align for that to happen. The problem with the non-randomized quicksort is that bad behavior is observed when the list is already sorted. And as we just said, it's very likely that you're going to encounter sorted lists to resort them. So you're sort of optimizing to get away from the bad behavior being commonplace. And that's kind of the lesson for today. So let's summarize. A lot of really elegant ideas in quicksort. This notion of divide and conquer is a powerful idiom for doing calculations on structures. We're going to see this again and again and again. It's a great idea of how a simple idea has many implementations. If you look at the YouTube quicksort, it has a different pivoting scheme. Pay special attention to who's wearing the hats because that tells you where the pointers are. It's actually pretty slick. And it's a great example of the notion of encapsulation, which we'll talk about when we talk about object-oriented programming, which is hiding something from the outside world. In this case, we have this secret helper function that can only be called from within quicksort. It's defined nowhere else. It's my private function for my quicksort algorithm. That's a very powerful notion in organizing code. And finally, it's a great example of how I can use non-determinism to improve performance. And these are one type of probabilistic algorithms. When we meet again on Wednesday, we're going to see another type of probabilistic algorithm, something called Buffon's needle. And that's a different kind of use of randomization, but that'll be our next topic. Okay. Have a good day, and we'll see you on Wednesday.